We have already understood about ridge regression, which is also called as L2 regularization. And a super important interview question may come that why do you use ridge regression? You basically have to say about it is basically used to reduce overfitting. Now, in this video, we are going to discuss about lasso regression. And lasso regression is also called as something called as L1 regularization. And why do we specifically use? We specifically use for a very important work that is called as feature selection. Now, how do we do feature selection and all? Let's discuss about this. Now, in lasso regression, we just need to focus more on the cost function. So here, the cost function is nothing but it is 1 by 2m summation of I is equal to 1 to m. And here, obviously, you have something called as h theta of x of I, which is my predicted point, y of I. Along with this, now we are going to add two more parameters. One is lambda, and the second one is something called as summation of I is equal to 1 to n, not slope square, but it should be magnitude of slope. Now, with the help of this specific equation, we will try to do some feature selection. Feature selection basically means the features that are not that important will automatically get deleted, and features that are very, very important, it will be considered. Now, if I try to show you the relationship between lambda and this slope, okay, with respect to this specific cost function. So suppose if I try to draw this cost function over here in the right hand side with respect to theta and j of theta by using this cost function, obviously the first one, if your lambda value is 0, I will be getting a normal curve, right? Normal gradient descent curve. So let's say this is my 0, or so let's say this is my, I'm just going to use this over here, 0, this is minus 0.2, and this is 0.2, 0.4, 0.6, 0.8, 1.0. Okay, so if I try to draw this kind of curve, this curve is called as gradient descent curve. With lambda is equal to 0, I'll be getting this kind of curve, right? And this is obviously my global minima. Now, what happens when my lambda value will increase? Then I will probably get my another curve which will look like this. Okay, and let me just draw this, and then everything will make sense. Okay, and then I may probably also get one more curve which may look like this, and finally I may get one more curve which will look like this, okay. Now, what is the difference between this curve and the previous curve when my lambda value is increasing? Let's say this green line is basically when lambda is equal to 10, this is lambda is equal to 20, this is lambda is equal to 40, let's say. Okay, now in this scenario, what happens is that obviously as I increase my lambda, my theta value is decreasing. But you will be seeing that after one point of time, my theta value will become 0. Okay, so this is nothing but this is basically becoming 0. So in short, my coefficient is actually becoming 0. Now, what happens if my coefficient actually becomes 0? In short, we are actually trying to remove that specific feature, right? So let's say my h theta of x is this specific equation, theta 0 plus theta 1 x1 plus theta 2 x2 plus theta 3 x3 plus theta 4 x4. Let's consider that I have 4 independent features. Let's say my theta 0 is 0.52. My theta 1 that I have probably computed by creating the best fit line is somewhere around 0.65 x1. This is 0.72 x2. This is 0.34 x3, and this is 0.12 x4. Now, in this particular scenario, you can see that x4 is the feature that is not much correlated with the output feature, that is with respect to h theta of x, because here why we have a very small coefficient, that is 0.12. So after we apply over here lasso regression, since this feature is not that important, what it will do is that it will try to reduce this coefficient to something like 0. Right, so 0 multiplied by x4 will actually become 0. So this will entirely become 0, and this all value will get reduced by a smaller number, 51 x1, because this is directly correlated, right? So this may be x2, this may be 0.14 x3, like this. So in this way, you can see that this feature is been removed, and we have not used this particular feature, or this coefficient has become 0 because this feature is not that important, right? So this is what basically indicates once we add this specific term in the cost function. right? Once we add this specific term in the cost function, we can see that what is the relationship between lambda and slope. So here, obviously your theta value is becoming less, but at one point of time, this will become 0. That is, your theta value will become 0. So the same thing is basically happening over here, which all features are not that much correlated. And if it is not correlated, then obviously it will be having a small coefficient value. So after we apply lasso regression, this will actually become 0. And by this entire feature is getting removed. And remaining all features is basically used to find out the best fit line, right? So this is the importance of lasso regression, right? And when we do use this, suppose if I have hundreds and hundreds of feature, right, I should definitely go ahead and use lasso regression, because automatically it will be able to find out features that are not that highly correlated. It will just try to remove it because it is going to make the coefficient to 0. Right? Similarly, when should we use ridge regression? It is very simple. Whenever overfitting condition basically happens, wherein your training data accuracy is very, very high and your test data accuracy is very, very low, this basically is an overfitting condition. So we should basically try to apply a ridge regression in this particular case. Right? Now coming to the next one, which is super, super important. What is ElasticNet? Right? ElasticNet is nothing, guys. It is the combination of both. So let me write this. With respect to ElasticNet, it is a combination of both ridge and lasso. So here, with the help of ElasticNet, what all things we do? First of all, we try to reduce overfitting. And the second one is that we try to, along with overfitting, what we do? We also do feature selection. So if I combine both ridge and lasso together, that actually becomes a ElasticNet. So what will be the cost function that may look like over here now? So I may basically write my cost function, which will look like this: 1 by 2m summation of I is equal to 1 to m, and this will be y of I minus y of, I'll not say y of I, but I'll say h theta of x of I, okay, minus y of I whole square plus, and we can basically use, for reducing overfitting, what do we use? We use lambda 1, and this lambda 1 we can basically multiply with summation of I is equal to 1 to n, and this will be my slope square, okay, and plus lambda 2 summation of I is equal to 1 to, I should not write n, instead I can also write m, okay, because m basically indicates all the slope parts, okay. So this will be slope. So what is basically happening? This reduces overfitting, okay, and this reduces, this actually helps us to perform feature selection. So this is for reducing overfitting, and this is for feature selection, right? So by this, we are trying to solve both the problems. Suppose if I have a model that is overfitting and it also have a lot of features, then I can directly use ElasticNet regression. Now, why do we learn all the series like ridge, lasso, and elastic? In short, we are hyperparameter tuning the linear regression. Okay, so hyperparameter tuning the linear regression, right? So we are basically hyperparameter tuning it. So that is the main reason why we are specifically using it. Okay, so yes, this was the series with respect to the regression, linear. Whenever you're using linear regression, you also need to think that when you should use ridge regression, lasso regression, and elastic regression. And I've seen many people asking different kind of interview questions with respect to this. Most important is what is the relationship between alpha and slope with respect to ridge and lasso. That both I've actually shown it to you, and how it performs feature selection and how it performs, how it reduces overfitting. Both has been discussed. So yes, let's continue. And in the next video, we are going to learn many more algorithms going ahead.